Your refrigerator seems pretty simple, right? I mean, it just makes things cold. But the actual secret behind how it works is this fascinating piece of physics that, get this, has nothing to do with creating cold at all. Let's dive in.
We all know what it does. You put a warm bottle of water in, and later it comes out cold. But what's actually happening in there? How does that box humming in the corner of your kitchen literally pull the warmth out of your food?
Well, the answer is so cool because it's not really about making cold in the first place. It's all about moving heat around. And to really get how your fridge pulls off this magic trick, we got to go back to some super basic physics.
All right, so to wrap our heads around how a fridge moves heat, we first need a quick little refresher on matter itself and, how it deals with energy. This is the foundation for, well, everything that comes next. So yeah, at a glance, we see three states we all learned about in school: solid, liquid, and gas. But the real action is happening down at the molecular level. Think of it like a dance floor. In a solid, the molecules are all packed in tight. Not a lot of energy, not much movement. In a liquid, they can kind of slide past each other. And in a gas, well, that's just a wild high-energy party. So, how do you get something to change from one state to another? It's pretty simple, actually. You just add or take away energy. If you want to melt ice or boil water, you add heat. If you want to freeze water or turn steam back into liquid, you got to take that heat away. It's a two-way street. Makes sense, right?
Okay, but here's a super important point we need to get straight. Heat and temperature are not the same thing. Heat is the actual energy. It's what makes those molecules dance around. Temperature, on the other hand, is just our measurement of how intense that energy is. They're related, for sure, but they are not the same.
All right, with those basics out of the way, now we can get to the really cool part. Literally, the secret sauce of refrigeration. The magic isn't just in the heat itself, but in what happens when matter changes its state, or its phase.
And this is where everything you thought you knew about heat gets a really interesting twist. It turns out heat has this kind of hidden superpower that's the key to this whole thing. So first up, we have the type of heat we all know and, well, feel. It's called sensible heat. And it's called that for a reason. You can literally sense it. You feel it as warmth, and you can see its effects on a thermometer. It's super straightforward. You take some water, let's say it's 10 degrees Celsius, and you start adding heat to it. What happens? The temperature goes up. That's sensible heat doing its thing. Plain and simple.
But here's the mind bender. What if I told you that you could add heat to something, and the temperature doesn't change at all? It sounds like it breaks the rules, right? But it happens all the time, and this is the secret we've been looking for.
So, let me introduce you to latent heat. The word latent literally means hidden, and that's the perfect way to think about it. It's this hidden energy that a substance absorbs just to make that big jump from one state to another, like from a liquid to a gas. This energy doesn't make things hotter. It's used for one thing and one thing only: breaking the molecular bonds that hold it together as a liquid. And you've absolutely felt this in real life. It's the perfect example. Think about putting hand sanitizer or rubbing alcohol on your skin. What happens? It feels cold, right? Like instantly cold. But why? Here's what's going on. For that alcohol to evaporate, to change from a liquid into a gas, it needs a burst of energy. It needs to suck up some of that latent heat. And where does it get it? From the closest source available, your skin. By pulling that heat energy away from your hand, it literally makes your skin colder. See? It's not creating cold, it's just moving heat. Okay, so how do we take that simple idea, alcohol cooling your hand, and scale it up to cool down an entire refrigerator? Well, it's all about taking that exact same process and putting it inside a closed loop. And that brings us to the official definition of refrigeration, which should make a whole lot more sense now. It's just the transfer of heat from one place to another by making a liquid change its state. That's it.
Let's break down the process. So, inside your fridge, you've got the special liquid, a refrigerant. Step 1, it absorbs that latent heat from all the stuff you put inside, your food, your drinks. Step 2, all that heat energy it just absorbed causes the liquid to boil and evaporate, turning it into a gas. And Step 3, that evaporation process is what actively cools everything down. Now, what's not on this slide is the other half of the journey. That gas, which is now carrying all the heat, gets pumped to the coils on the outside of your fridge. There, it releases all that heat into your kitchen, turns back into a liquid, and gets ready to start the whole cycle all over again.
So, what's the big takeaway here? What's the main thing to remember? It really changes how you think about that big humming box in your kitchen.
All right,
If you take away just one single thing from all this, let it be this.
Your refrigerator doesn't create cold. It's not a cold-making machine. It's a heat-moving machine. It grabs heat from the inside and literally pumps it out into your kitchen. The cold you feel is just what's left behind when heat is gone.
And that really leaves us with a final thought. Once you understand this principle, that cooling is just evaporation, moving heat, you start seeing it everywhere. It's in your air conditioner. It's even in how our own bodies sweat to cool us down. So the next time you feel that chill, you'll know exactly what's going on. It's not about making cold, it's all about moving heat.